Hello students and welcome. Now, we already know that a single resistor can control the flow of electricity in a circuit. But what happens when we need to use more than one? Today we are going to dive into the very interesting topic of combining resistors, and we will see how different connections can lead to very different results. So, here is our plan for today's lesson. We will start by asking a basic question. Why do we even need more than one resistor? Then we will explore the two main ways to connect them, one after another, which is called a series circuit, and with multiple branches, which we call a parallel circuit. After that, we will compare them side by side, we will solve a practice problem, and finally, we will see how these very ideas are working right now to power your own home. All right, let's get started. Before we get into combining resistors, let's just quickly refresh our memory on what resistance actually does. This will help us understand the main question for today. Remember, resistance is basically like a friction for electricity. It's the property that slows down the flow of electrons. Now, in the real world, circuits are not so simple. Your phone, your TV, they all have multiple resistors working together, and there are two fundamental ways we can connect them. In series, which you can think of as a single-lane road, and in parallel, which is more like a big highway with many lanes. Okay, so let's explore our first method, connecting resistors in series. You will find that this one is quite easy to understand. Please take a look at the diagram on this slide. In a series circuit, you can see the resistors are connected end to end, one after the other, just like the bogies of a train. You can imagine the electricity as the train itself. It must pass through every single bogie, one by one. There is no other track it can take. This single path, this is the main feature of a series circuit. Now, this is the most important point to remember about series circuits. Since there is only one path for the electricity to flow, the amount of current is the same at every single point in the circuit. The current that flows through the first resistor is the exact same current that flows through the second one, and the third one, and so on. The current is constant everywhere.
So if the current is the same everywhere, what about the voltage? Well, the total voltage from the battery, it gets shared or divided among the resistors. You can think of it like a chapati that is being shared. Each resistor gets a piece of the total voltage. We call this a voltage drop. So, if you add the voltage drop across each resistor, you will get the total voltage of the battery.
Now, let's see how we can calculate the total resistance, or the equivalent resistance, of a series circuit. We can derive the formula together step by step. First, we start with our voltage rule. The total voltage V is equal to V1 plus V2 plus V3. Good. For step 2, we will use Ohm's law, which is V equals IR. We apply this to each part of our equation. This gives us IR total is equal to IR1 plus IR2 plus IR3. Now for the simple part in step 3. Since we know the current I is the same everywhere, we can just cancel it from both sides of the equation. And what does that leave us with? Our very simple and neat final formula. The total resistance in series, R series, is just the sum of the individual resistances.
So what is the main takeaway here? It's quite simple, really. In a series circuit, every time you add another resistor, you are just adding more opposition to the flow of current. So the total resistance will always be greater than even the biggest single resistor in the circuit. You are making the path harder and harder for the electricity. All right, so we have understood the single path of series circuits. Now let's see what happens when we give the current some choices. This brings us to our second method of connection, resistors in parallel. It is a bit different, but you will see it is also very logical. Look carefully at this diagram. In a parallel circuit, you can see all the resistors are connected across the same 2 points, X and Y. A good way to think about this is like a river that splits into several smaller streams. The total flow of water, it divides among the different streams. In the very same way, the total electric current from the battery splits up and flows through each of these parallel branches. And here, we come to the biggest difference between parallel and series circuits. Because all the resistors are connected between the same 2 points, the voltage across each and every one of them is exactly the same. Each branch in a parallel circuit receives the full, undivided voltage from the battery. This is a very important point, so please remember it. So, if the voltage is the same everywhere, what about the current? Well, let's go back to our river example. The total current flows towards a junction, and then it splits up. Some current goes down the first path, some down the second, and so on. After passing through the resistors, all those separate currents meet again and join back together. So the total current from the battery is simply the sum of the currents in each individual branch. Now, let's derive the formula for total resistance in a parallel circuit. This time, we will start with our rule for current. Total current I is equal to I1 plus I2 plus I3. Then, we use Ohm's law, but this time, we will write it as I equals V divided by R. We apply this to every term. Now, you see, since the voltage V is the same for every branch, we can simply cancel it out from the equation. This gives us our final formula. But please pay close attention. It is 1 over the total resistance Rp equals 1 over R1 plus 1 over R2, and so on. We are adding the reciprocals of the resistances. This is quite different from the series formula.
This formula, it leads to a very interesting and maybe a bit surprising result. The total resistance in a parallel circuit is always less than the smallest single resistor in the circuit. I know, it might sound a little bit strange, but think about it. By adding more and more paths for the current to flow, you are actually making it easier for the electricity to pass through. You are reducing the overall opposition. Just like more lanes on a highway means less traffic jam.
So, we have explored the single-path series circuit and the multi-path parallel circuit. Now, for making things very clear in our minds, let's put them side by side for a direct comparison.
This table summarizes everything perfectly. You can see how series and parallel are almost mirror opposites. In series, current is the same everywhere, but voltage is divided. In parallel, it's the opposite. Voltage is the same across all branches, but the current is divided. And look at the total resistance. In series, it just adds up and becomes bigger, but in parallel, it actually becomes smaller. The examples are also perfect. Old Diwali lights were often in series. That is why if one bulb fused, the whole string would stop working. But our homes are wired in parallel. That's why you can switch off one light and your fan keeps running.
Excellent. You now understand the theory, so it is time to put this knowledge to practice. Let's solve a problem together, just like one you might see in your examinations. Okay, here is the problem. We have 3 resistors. One is 5 ohms, one is 10 ohms, and one is 30 ohms. They are all connected in parallel to a 12-volt battery. Our task is to find the total, or the equivalent, resistance of this circuit. Let us solve this step by step. First, we must identify the type of circuit. It says they are in parallel. Second, we select the correct formula, which is the one with the reciprocals. Third, we put in the values, 1 by 5 plus 1 by 10 plus 1 by 30. Now it is just mathematics. We find a common denominator, which is 30, and we add the fractions. We get 10 divided by 30, but wait, we are not finished. This is the most common mistake students make. This is the value for 1 over the total resistance. To get the final answer, we have to flip it. We take the reciprocal. So the total resistance is 30 divided by 10, which is 3 ohms. And you can see, just as we learned, 3 ohms is smaller than our smallest resistor, which was 5 ohms.
So, we have done all this theory and mathematics. But you might be thinking, when will I ever use this? Well, the truth is, you are using it right now. Let's look at the most important real-world application of parallel circuits, the electrical wiring in your home.
This slide tells us exactly why parallel circuits are so useful. Think about your house. Everything is wired in parallel. Why? First, so that if one bulb fuses, the other lights and fans continue to work. Each appliance is on an independent branch. Second, so that every single appliance, from a small phone charger to a big geyser, gets the full voltage it needs to work properly. And finally, it allows each device to draw only the amount of current that it needs, no more and no less.
So, to finish our lesson, I will leave you with a final question to think about. Based on everything we have learned today, why would it be a very, very bad idea to connect a small lamp and a powerful room heater together in the same series circuit? What do you think would happen? Give it some thought. I hope this lesson has made the world of series and parallel circuits much clearer for you. Thank you for your attention.